really mind-bending territory, the universe's extremes.
Absolutely. The places where physics gets really weird.
Exactly. We're talking about black holes and wormholes. Now, both of these concepts, they actually spring from Einstein's theory of general relativity, right?
Yeah.
From 1915. Look at how they're similar, but also fundamentally different. We want to give you a clear picture.
A solid understanding of what the physics actually tells us about each one.
And key to this whole thing is remembering how Einstein saw gravity, not as a force pulling things, but
Yeah.
as space-time itself bending, warping.
Right. Like a bowling ball on a trampoline, curving the fabric around it. Black holes and wormholes are just extreme versions of that curvature, really extreme.
So where do we start with their shared origin? How does Einstein's work give birth to both?
It all boils down to the Einstein Field Equations, the EFE.
Okay.
These are 10 equations, very complex, interconnected equations, and they basically lay out the fundamental relationship in general relativity.
Which is?
How the geometry of space-time, its shape, its curvature is determined by the mass and energy within it. And conversely, how that space-time curvature tells matter and energy how to move.
So stuff tells space-time how to curve, and space-time tells stuff how to move.
Exactly. It's this beautiful, self-consistent picture, a geometric theory of gravity, completely different from Newton's idea of a mysterious force acting at a distance.
And when physicists talk about finding a solution to these equations, what does that mean practically?
A solution is basically a specific mathematical description. It's called a metric that shows what space-time looks like under certain conditions, like what's the geometry around a star or inside an empty, expanding universe. And what's really fascinating is you can find solutions even for empty space. A vacuum. These aren't trivial. They describe self-sustaining warps in space-time itself.
And that relates to black holes.
Precisely. The simplest black hole models are vacuum solutions. It shows space-time isn't just a stage, it's an active player with its own structure, its own dynamics.
Wow. Okay, so right after Einstein published his theory, someone actually found one of these solutions.
Almost immediately, Carl Schwarzschild, a German physicist in late 1915, found the first exact, non-trivial solution. It described the space-time geometry around a perfectly spherical, non-rotating, uncharged mass.
The simplest possible case, basically.
Exactly. And this Schwarzschild solution became the absolute foundational model for the simplest type of black hole, the vanilla black hole, if you like.
But here's where it gets really interesting, isn't it? This single solution held the key to both concepts.
That's the kicker. When you take the mathematics of the Schwarzschild solution and you analyze it fully, push it to its logical extremes, you find it describes not just the exterior of a black hole and its interior, but it also mathematically contains a structure connecting two regions of space-time, a sort of bridge.
The Einstein-Rosen bridge.
That's the one, a non-traversable wormhole. So this one elegant solution, derived so early on, contained the seeds for both a black hole and a wormhole. They're mathematically intertwined in this idealized scenario.
That is truly mind-blowing. The same math describes a trap and a potential tunnel. So let's dig into what defines these things, singularities and horizons. What exactly is a singularity in this context?
A singularity is, well, it's where the physics breaks. It's a point, or in some cases a ring, in space-time where quantities like space-time curvature and density mathematically become infinite.
Infinite, like literally infinite.
According to general relativity, yes. All the matter that collapses to form the black hole gets crushed into a region of zero volume and infinite density. That's the prediction.
But that sounds impossible, physically.
It likely is. The existence of singularities is probably the strongest signal we have that general relativity isn't the final word. It breaks down at these extreme points. We need a deeper theory, probably quantum gravity, to truly understand what happens at the center of a black hole or at the Big Bang.
Okay, so the singularity is this point of breakdown. What about the event horizon? That's the famous part.
The event horizon is really the defining feature of a black hole. It's not a physical surface you could bump into, but rather a boundary in space-time, a one-way membrane.
The point of no return.
Exactly. Its size is defined by the Schwarzschild radius, a distance from the center where the escape velocity equals the speed of light. If you cross that boundary, you can't get out.
Why not? Can't you just fire your rockets?
No, because inside the horizon, space-time itself is warped so extremely that all possible paths, all future directions, inevitably lead towards the central singularity. Space itself flows inward faster than light can flow outward. There's literally no direction you can point that leads back out.
Wow. Space flows inward. That's hard to grasp. Now, you mentioned the math looks weird at the horizon in some descriptions. Is that a real issue?
Ah, good point. In
Hmm.
the original Schwarzschild coordinates, yeah, the math looks like it blows up, goes infinite at the horizon. But that's just an artifact of the coordinate system, like the way longitude lines converge crazily at the North Pole on a map.
So it's not a real physical singularity there.
No, not at all. Space-time at the event horizon is actually perfectly smooth, locally flat even. We can use other coordinate systems like Eddington-Finkelstein or Kruskal-Sekker's coordinates that completely remove that mathematical weirdness and show a smooth transition across the horizon.
Okay, so the horizon is smooth passage, but the center is where the real problem, the physical singularity, lies.
That's the crucial distinction. The coordinate singularity at the horizon is just math. The physical singularity at R0, the center, is where GR predicts infinite curvature and density, and that's the real breakdown.
And these other coordinate systems, like Kruskal-Sekker's, they reveal more about the overall structure.
They do. The Kruskal-Sekker's diagram maps out the maximally extended Schwarzschild spacetime. It's quite remarkable. It shows not just our universe and the black hole interior, but also a region called a white hole interior. Think of it like a time-reverse black hole. Things can only come out, and a whole separate, second, asymptotically flat region, another universe, mathematically speaking.
Universe connected.
Connected through that Einstein-Rosen bridge, yes. That mathematical structure links the two exterior regions in this idealized eternal black hole solution.
Okay, and this feels like a big but, how does this idealized picture relate to the black holes that actually form in our universe?
Exactly. This is the critical distinction. This four-part structure describes an eternal black hole, one that has supposedly existed forever.
Hmm,
Real astrophysical black holes aren't like that. They form at a specific time from the collapse of a star.
right.
And the very process of formation, the collapsing matter itself, effectively changes the structure. It essentially plugs up the would-be white hole and the connection to the other universe. Ah, okay, so the black holes we actually see out there formed from stars.
They are not predicted by general relativity to contain an Einstein-Rosen bridge or a white hole exit. The wormhole part of the idealized solution gets pinched off by the formation process. So observed black holes are just one-way trips to a singularity.
That makes a huge difference. So the wormhole idea, while mathematically linked in that first simple solution, isn't expected in real black holes.
Correct. That separates the confirmed reality of black holes from the purely theoretical nature of wormholes quite fundamentally.
Right, let's focus on that confirmed reality then. The black hole as this gravitational abyss. What does an active black hole look like? If we were observing one, what are the key parts from the outside in?
Okay, so if it's an active one, meaning it's feeding, the most prominent feature is usually the accretion disk.
Right, the swirling gas.
Exactly. Gas and dust get pulled in from a companion star or surrounding clouds. But because of angular momentum, it doesn't fall straight in. It forms this flattened, rapidly spinning disk.
And it gets hot. Incredibly hot. Millions, even billions of degrees. Friction within the disk plus powerful magnetic fields heat the material up until it glows fiercely across the spectrum: radio, optical, UV, X-rays. It's one of the ways we find them.
And parts of it look brighter.
Yeah, due to relativistic effects, Doppler beaming the side of the disk spinning towards us appears significantly brighter and bluer, while the side spinning away looks dimmer and redder.
Okay, what's next as we move closer?
Just outside the event horizon, there's a region called the photon sphere. This is at about 1.5 times the Schwarzschild radius.
And what happens there?
Gravity is so strong here that photons, light particles, can actually orbit the black hole. It's an unstable orbit, mind you. A photon could zip around a few times, but the slightest nudge sends it either flying away or spiraling into the horizon.
So light can orbit it. Wow. Does that contribute to what we see?
Yes, it contributes to the appearance of the bright photon ring right at the edge of the black hole's shadow in those EHT images.
Speaking of which, the event horizon and its shadow, the horizon itself is invisible, right?
Completely invisible. Nothing escapes, not even light. But its presence is dramatically revealed by the shadow it casts.
How does that work?
The black hole itself is dark, but it's silhouetted against the bright background of the accretion disk or other light sources behind it. Because of extreme gravitational lensing light bending around the black hole, this shadow actually appears larger than the event horizon itself, roughly twice the diameter.
And that shadow is what the Event Horizon Telescope imaged.
Precisely. That dark central region in the M87 and Sagittarius A images is the shadow of the event horizon.
And then, deep inside all that,
At the very center lies the singularity, the theoretical point of infinite density where everything that crosses the horizon must ultimately end up, and where our current understanding of physics fails.
Okay, let's imagine watching something fall towards the horizon from far away. What relativistic effects would we see?
Two really dramatic ones. First, gravitational redshift. As light climbs out of the black hole's deep gravity well, it loses energy.
Like climbing a hill.
Sort of, yeah. This loss of energy stretches the light's wavelength, shifting it towards the red end of the spectrum. So an object falling in would appear redder and redder, eventually shifting out of visible light into infrared, then microwaves, then radio waves, becoming progressively fainter until it disappears.
And the second effect? Time itself.
Gravitational time dilation. To you, the distant observer, time on the falling object would appear to slow down dramatically as it approaches the horizon.
Slow down, like its clock ticks slower.
Yes, slower and slower. Its movements would seem to decelerate, almost grinding to a halt as it gets closer and closer to the horizon. From your perspective, you'd never actually see it cross. It would appear to freeze, dimmer and redder, right at the boundary, taking infinitely long to actually fall in.
So from the outside, it looks frozen forever. But for the object itself?
For the object itself, time passes normally, and it crosses the horizon in a finite time, meeting its fate inside. It's one of those bizarre consequences of relativity. Time is relative.
Chilling. Okay, how do these things actually form? The stellar mass ones, anyway.
The most common way we think they form is from the death of very massive stars. Stars much bigger than our sun, say, over 20 times its mass initially.
What happens when they die?
When they run out of nuclear fuel in their core, the outward pressure from fusion stops holding them up against their own immense gravity.
And gravity wins.
Big time.
Yeah.
The core collapses catastrophically, incredibly fast fractions of a second. This implosion triggers a massive shock wave that travels outwards, blowing the star's outer layers apart in a spectacular supernova explosion.
Leaving the core behind.
Right. And the fate of that remnant core depends on its mass. If it's more than about 2 to 3 times the mass of the sun, what's called the Tolman-Oppenheimer-Volkoff limit, then no known force in nature, not even the pressure of neutrons crammed together, can stop gravity from crushing it further. It collapses indefinitely, forming a singularity shrouded by an event horizon. A black hole is born.
So a massive star dies, explodes, and leaves behind a black hole if the core is heavy enough.
That's the standard picture for stellar mass black holes, yes.
What about the monsters in galaxy centers? The supermassive ones.
Their origin is still debated, actually. They might have formed from the direct collapse of enormous gas clouds in the very early universe, long before stars and galaxies as we know them.
Skipping the star phase entirely.
Possibly, or they could have started as smaller black holes, maybe from the first stars, and then grew over billions of years by gobbling up gas, dust, stars, and merging with other black holes. Probably a combination of processes.
Okay. Now the terrifying part. Falling in. Spaghettification. It sounds like something out of a cartoon, but it's real physics.
Oh, it's very real physics.
Yeah.
And the name is surprisingly descriptive, but the key isn't just how strong gravity is, it's the difference in gravity across an object. The tidal force.
Tidal force. Like the moon causes tides on Earth.
Exactly the same principle, just ramped up insanely. Imagine you're falling feet first towards a black hole. Your feet are closer to the singularity than your head is. So the gravitational pull on your feet is significantly stronger than the pull on your head. This difference in force stretches you vertically.
Stretches you. Okay.
At the same time, gravity pulls everything towards the center point. So forces are also pulling your sides inwards, squeezing you horizontally.
So stretch vertically, squeeze horizontally.
Yep. The net effect is you get drawn out into a long, thin strand of atoms, like spaghetti. Eventually, the tidal forces become strong enough to rip apart molecules, atoms. It's not a pleasant end.
Definitely not. Now, here's something that seems weird. Does the size of the black hole affect when this happens?
It does, and it's completely counterintuitive. The strength of the tidal force at the event horizon is actually weaker for more massive black holes. It's inversely proportional to the mass squared.
Weaker for bigger black holes.
Think about it. For a small stellar mass black hole, maybe 10 times the sun's mass. The event horizon is tiny, only maybe 60 kilometers across. The distance from the horizon to the singularity is short, so the gradient of gravity, the difference in pull over a short distance, is incredibly steep right near the horizon.
Okay.
So for a stellar mass black hole, an astronaut would encounter lethal tidal forces, spaghettification, thousands of kilometers before even reaching the event horizon. You'd be torn apart long before you got to the point of no return.
Wow. Okay, so what about a supermassive one, like millions or billions of solar masses?
For a supermassive black hole, the event horizon is enormous. It could be bigger than our solar system. Because it's so huge, the distance to the singularity is vast. The change in gravity across, say, an astronaut's body near the horizon is much, much gentler.
So
So you could actually cross the event horizon of a supermassive black hole without feeling much tidal force at all. You might not even notice you'd passed the point of no return.
you could just float across.
Initially, yes. The ride across the boundary itself will be relatively smooth. Of course, your fate is sealed. You are falling towards the singularity, and the tidal forces will become immense, much deeper inside, closer to the center. But you cross the horizon intact.
That's bizarre. Safer initially to fall into a bigger black hole. Mind-bending.
Okay, but this isn't just theory. We know these things exist. What was the early evidence?
For a long time, the evidence was indirect, but very compelling. Astronomers started tracking stars orbiting the very center of our Milky Way galaxy.
Like the star S2.
Exactly. S2 orbits something invisible incredibly fast. By precisely measuring its orbit over decades, we could calculate the mass of the unseen object it's circling.
And the result?
About 4.3 million times the mass of our Sun, all crammed into a region smaller than Mercury's orbit. The only thing we know that can be that massive and that compact is a supermassive black hole. That object is Sagittarius A.
Okay, that's strong evidence for the big ones. What about smaller, stellar mass black holes? We found many of those in X-ray binary systems. These are pairs where a normal star orbits an invisible companion.
How do we know the companion's a black hole?
First, you measure the normal star's orbit to figure out the companion's mass. If the invisible object's mass is more than about 3 solar masses, that's too heavy to be a neutron star, the other possible dense remnant, then it's a strong candidate for a black hole.
And the X-rays.
If the invisible companion is pulling gas off the normal star, that gas forms an accretion disk, gets superheated, and emits intense X-rays. Seeing those X-rays from a system with a heavy, invisible companion is smoking gun evidence. Cygnus X1 was the first big confirmation back in the early 70s.
So orbital dynamics and X-rays gave us the first real proof, but then things got much more direct, didn't they?
Oh, yeah. The game changed completely in 2015 with LIGO, the Laser Interferometer Gravitational Wave Observatory.
Gravitational waves, ripples in space-time itself.
Predicted by Einstein a century earlier, LIGO detected this tiny chirp signal, GW150912, and it perfectly matched the theoretical prediction for 2 black holes, one about 29, the other 36 solar masses spiraling into each other and merging into one bigger black hole, about 1.3 billion light-years away.
So we didn't just detect the waves, we heard black holes colliding.
Effectively, yes. It was the first direct detection of gravitational waves and the first direct observation of black holes merging. A monumental discovery. And since then, LIGO and its partners have detected hundreds more mergers of black holes and neutron stars. It's opened a whole new way to see the universe.
Incredible. And then the ultimate proof. Actually seeing one.
The visual confirmation. That came in 2019 from the Event Horizon Telescope collaboration, the EHT.
How did they manage that? Black holes are tiny and dark.
By using a technique called Very Long Baseline Interferometry, or VLBI, they linked radio telescopes all across the Earth, effectively creating a virtual telescope the size of our planet. This gave them the incredible resolution needed.
And they pointed it at
M87, the supermassive black hole in the center of the galaxy, Messier 87, about 55 million light-years away. It's a real giant, about 6.5 billion times the sun's mass.
And the image showed.
It showed exactly what theory predicted. A bright, asymmetric ring of light, the lensed emission from the hot accretion disk surrounding a dark central region. The black hole's shadow.
The shadow we talked about earlier.
Precisely. The size, the shape, the asymmetry of the ring, it all matched general relativity's predictions remarkably well. It was stunning visual confirmation. They've since imaged Sagittarius A, too. Black holes went from mathematical curiosity to observed reality.
Amazing journey. Okay, let's pivot now.
Yeah.
From the confirmed abyss to the hypothetical bridge.
All right.
The wormhole, here's where speculation takes over, right? We mentioned the Einstein-Rosen bridge earlier.
Yeah.
Why isn't that usable?
Right. The original wormhole found in the Schwarzschild math. It has 2 major problems that make it completely impractical. First, instability.
It collapses.
Extremely quickly. Wheeler and Fuller showed back in 1962 that this bridge isn't static. It pinches off so rapidly that even light doesn't have time to get through before it slams shut into a singularity.
So it closes faster than light can cross it. Wow. What's the second problem?
Even if you could somehow magically hold it open, it's still non-traversable in the useful sense. If you trace the paths, the causal structure, going into the bridge from our universe,
Yeah.
you find that all paths traveling at or below light speed end up hitting a future singularity. You can't actually emerge into the other universe region without exceeding the speed of light.
So it's unstable and a one-way trip to a singularity anyway, a cosmic dead end.
Pretty much, yeah. The original Einstein-Rosen bridge is fascinating mathematically, but it's not a viable transport system.
So how did we even get the idea of traversable wormholes, the kind you see in sci-fi for zipping across the galaxy?
That came much later, driven partly by fiction, actually. Carl Sagan wanted a plausible way for his character in the novel Contact to travel interstellar distances quickly. He asked Kip Thorne, a prominent relativist.
And Thorne.
Thorne and his student Michael Morris decided to work backward. Instead of finding wormholes in existing solutions, they asked, what properties would a wormhole need to have for safe, two-way human travel? And then what kind of physics, what kind of matter or energy could create such a space-time geometry?
Okay, so engineering a wormhole on paper, what were the must-have features?
They laid out some key requirements. First, crucially, no event horizons. You need to be able to go in and come back out.
Right, two-way travel.
Second, it has to be stable, held open against the natural tendency of gravity to make it collapse. Third, the tidal forces inside the throat connecting the two mouths must be gentle enough not to kill a traveler less than one given, ideally.
No spaghettification allowed.
Definitely not. And finally, it has to actually be a shortcut. The travel time through the wormhole needs to be reasonably short, and shorter than going the long way through normal space.
That sounds like a very demanding wish list. What did they find you'd need to build such a thing?
This is where it gets really problematic. They found that to keep the throat of such a wormhole open, you need something that creates repulsive gravity.
Repulsive gravity, like anti-gravity.
Effectively, yes. Normal matter and energy curve space-time in a way that's attractive. To prop open a tunnel against this attraction, you need matter with a very large negative pressure. So large, in fact, that it violates what physicists call the null energy condition.
Negative pressure.
Yeah.
Negative energy. What is that?
It essentially means matter with a negative energy density, or at least pressure so negative it overcomes the positive energy density. This stuff is often called exotic matter. And Morris and Thorne proved that any traversable wormhole consistent with general relativity absolutely requires this exotic matter threading through its throat to keep it stable.
Exotic matter. Does that stuff exist? Have we ever seen any?
That's the billion-dollar question. And the answer is not really, not in the amounts needed. There's one theoretical place where negative energy densities can appear. The Casimir effect in quantum field theory.
The Casimir effect.
Yeah, it's a real measured effect where if you place two metal plates very close together in a vacuum, the quantum fluctuations between them are suppressed, leading to a slightly lower energy density between the plates compared to outside. This creates a tiny attractive force, so you get negative energy density relative to the vacuum outside, but only tiny amounts over microscopic distances.
So not enough to hold open a spaceship-sized tunnel.
Not even close. Orders and orders of magnitude too small. Some people look at modified theories of gravity, where maybe you could have wormholes without exotic matter, but those theories are themselves highly speculative and untested.
So the bottom line is, we have no evidence that the kind of macroscopic exotic matter needed to build a stable traversable wormhole actually exists in our universe.
That's the current situation, yes. It makes traversable wormholes seem less like a natural possibility and more like a purely theoretical engineering project where the required building material might be physically impossible to obtain. It's the biggest hurdle by far.
A potential showstopper, as you said. Given all that, is there any point even looking for them? How would we detect one if it somehow did exist?
Well, people have thought about it, even though it's a long shot. One potential signature is through gravitational lensing.
Like with black holes.
Sort of, but different. Because the exotic matter would be gravitationally repulsive, a wormhole mouth might have a unique anti-focusing effect on light from stars behind it. Instead of just making the star brighter, it might cause a distinct pattern, like brightening, then dimming, then brightening again as it passes.
Interesting. Anything else?
There are other ideas. Maybe unique radiation signatures. Some theories predict phantom radiation, or a different type of Hawking radiation compared to black holes, or perhaps subtle differences in how an accretion disk around a wormhole mouth would look, differences in the light polarization or specific spectral lines.
But these would be hard to spot.
Extremely hard. And given we have zero evidence they exist and the theoretical hurdles are so high, it's very much on the fringes of observational searches. You'd have to rule out all other explanations first.
Okay, let's bring it all together now. We've got the black hole, the abyss, and the wormhole, the hypothetical bridge. What are the absolute core take-home distinctions?
I think the first is their origin in the theory. Black holes are a natural, almost unavoidable prediction of general relativity when gravity gets strong enough with normal matter. Wormholes, the traversable kind, are artificial engineered solutions that require breaking standard energy conditions with hypothetical exotic matter.
Natural versus engineered. Got it. What about their structure?
Fundamentally different topology. A black hole is a one-way trap. It has an entrance, the horizon, but no exit to another place or time, leading only to a singularity. It's a dead end. A traversable wormhole is, by design, a two-way bridge. No horizon, no singularity in the throat, connecting two different points in spacetime. It's a handle, a shortcut.
Prison versus portal.
Good way to put it. Then there's stability. Black holes are stable structures. Once formed, they stick around. The original Einstein-Rosen bridge is catastrophically unstable. Traversable wormholes require continuous, active stabilization by that non-existent, exotic matter.
Stable versus fundamentally unstable or needing impossible support.
Right. And finally, and most importantly from a scientific perspective, observational status. Black holes are confirmed. We have overwhelming diverse evidence orbits, X-rays, gravitational waves, direct images. Wormholes are purely hypothetical. Zero observational evidence whatsoever.
Confirmed reality versus speculation. That seems pretty clear-cut.
It really is. Despite their shared roots in GR's geometry, they end up being vastly different concepts in terms of physical plausibility and observational standing.
So recapping the fundamentals, black holes are natural, stable, observed, one-way traps born from gravity-crushing normal matter. Traversable wormholes are artificial, require exotic matter we haven't found, are speculative, and designed as two-way tunnels.
That sums it up well, and both concepts really push our understanding. The singularity inside black holes tells us loud and clear that general relativity isn't complete. It's a signpost pointing towards the need for quantum gravity.
We need that deeper theory to understand those extremes, and the Big Bang, too, presumably.
Absolutely. And interestingly, quantum physics, while not providing macroscopic exotic matter, does offer these tiny hints like the Casimir effect. And then there are even wilder ideas.
Like what?
Well, there's a highly speculative conjecture in theoretical physics called ER-EPR.
ER-EPR. What does that mean?
ER stands for Einstein-Rosen bridge, the wormhole. And EPR refers to Einstein, Podolsky, and Rosen's famous paper on quantum entanglement, spooky action at a distance.
Okay.
The conjecture suggests that maybe these two concepts are deeply linked, that a wormhole, ER, might be the geometric description, the gravitational dual of quantum entanglement, EPR.
So every pair of entangled particles is connected by a tiny wormhole.
That's the radical idea. If true, it would mean microscopic, non-traversable wormholes are everywhere, underpinning quantum entanglement. But these wouldn't be shortcuts for us, just a deep connection between gravity and quantum mechanics. Very speculative, but fascinating.
Wow, that's a wild thought. So looking ahead, how do we keep probing these mysteries? What's next?
We need better eyes and ears. Next-generation observatories like an upgraded Event Horizon Telescope, an EGHT, more sensitive gravitational wave detectors like LIGO Voyager or the Einstein Telescope, LISA in space.
What will they allow us to do?
They'll give us much more precise measurements of the spacetime right near black hole event horizons. We can test general relativity in these extreme gravity environments with unprecedented accuracy. We'll look for tiny deviations from GR's predictions that might hint at quantum gravity effects or other new physics.
And maybe, just maybe, spot something unusual.
On the very, very long shot front, yes. If wormholes did exist and had those predicted unique lensing or radiation signatures, these supersensitive instruments would be our best bet, however unlikely, to potentially detect them.
So for everyone listening, what's the final thought here? What should we take away from this deep dive?
I think it's this. The confirmed reality of the black hole is a stunning triumph for Einstein's general relativity. It shows how well we understand gravity, even in its most extreme forms. It validates our current physics.
But the wormhole.
The speculative possibility of the wormhole, even though it seems to require impossible ingredients right now, does something else. It pushes us to imagine what might lie beyond our current understanding. It fuels the quest for new physics, for quantum gravity, for whatever comes next.
So one anchors us in confirmed knowledge. The other propels us toward the unknown future of cosmic discovery.
Exactly. One tells us what gravity is, the other makes us dream about what else space-time might be able to do.